Hello, ladies and gentlemen. Today we are going to take a look at special right triangles. So what makes a triangle special? And then also we're going to take a look at how the fact that he's a special right triangle helps us determine missing sides. So we're going to look at relationships between sides in special right triangles, and that's going to allow us to find missing pieces of a triangle. So we're going to need your notes as well as something to write with and a calculator today. All right, let's go ahead and identify first that there are two types of special right triangles that we work with quite a bit in geometry as well as pre-calc, algebra 2, math beyond this point, okay? So the first one is called a 45, 45, 90-degree triangle. And that is based on the angles that you would see in that triangle. And we also have a 30, 60, 90-degree triangle. Those are two types of triangles that we consider special right triangles. Now remember, with a 45, 45, 90-degree triangle, we would be talking about the angles 45, 45, and 90. And also within a 30, 60-degree triangle, we would be talking about the angles there as well. 90, the 30-degree angle, a little bit smaller here than the 60-degree angle. All right, so these are the two types of special right triangles we're going to look at in this video. First, we're going to start with the 45, 45, 90-degree triangle. This is the part of the video that I just want you to watch as we develop this relationship and understanding how the sides work. So let's first start by having a 45, 45, 90-degree triangle here. I'm going to add some numbers to my picture. We have the 90-degree angle and we have two 45-degree angles. Now I'm just going to name one of the legs with the generic variable like A. Now if this leg is A, remembering the fact that we have two equal angles in this triangle means that I do have an isosceles triangle here. If this side length is in fact A, then the other leg would also have that same length of A, because this triangle is isosceles. So if those two sides are both A, then if I wanted to find the hypotenuse, let's say if I generically call it C, we would go ahead and set up the Pythagorean theorem to help us find this hypotenuse. So I'd say A squared plus A squared would equal C squared. Now if you have A squared plus A squared, you really have 2A squared equals C squared. And now remembering what we do here to get the C alone to solve for the hypotenuse, I would take the square root. I would take the square root on this side. So I'd have the hypotenuse, or the C, is equal to the square root of 2A squared. Now how do we square root that? Well, I cannot square root of 2, so I'll leave that portion alone. But the square root of A squared would just be A. So this is telling me that the hypotenuse, the C on my triangle relationship, is the same as square root of 2 times the A. So I'm going to just scribble out this C here and say that the hypotenuse is the square root of 2 times A, or I would write as the A in front of the square root of 2, either way, okay? So notice that if I know a leg, like if this A is 5, I can use that fact to help me find the hypotenuse a lot faster by knowing the relationship here. So whatever the legs are, the hypotenuse is going to be the leg times the square root of 2. So if the legs are 6, the hypotenuse is 6 times the square root of 2, or 6 square roots of 2. So understanding that relationship, let's go ahead and get that part in your notes. So in a 45, 45, 90-degree triangle, the hypotenuse will always equal the leg times the square root of 2. So please make sure you get that part in your notes, and then let's go ahead one more time and write a picture of a 45, 45, 90-degree triangle in there. And remember that these two are the legs, and the hypotenuse would equal whatever that leg is times the square root of 2. Okay, I'm going to give you a minute to write that part down, and then let's take a look now at our 30, 60, 90-degree triangle. So again, first I want you to just watch the relationship and how that's built, and then we'll go ahead and write down what we discover here into our notes. So again, let's start with the fact that a 30, 60, 90-degree triangle has a right angle, a 30-degree angle, and a 60-degree angle. And just like the last relationship, we're going to start with just calling a generic leg here A. And I'm going to call A this short leg, the shorter of the two legs here on my 30, 60, 90 degree triangle. So I'm going to just duplicate that over here a little bigger so I can write on it, and then we'll keep track of what's happening on that one on the right. So the short leg is A. Now, I'm just going to, for understanding the relationships, what I'm going to do now is actually duplicate or reflect this triangle to the other side. So I'm just going to make a mirror reflection here to understand the relationship here and how this works. That's kind of a rough reflection there. But if I reflect this triangle, then up here would be another 30 degrees, and here would be 60 degrees. And notice how my little side A has now gone reflected to the other side, making this A as well. So if I wanted to generalize here, I'd say the base here of my reflected triangle and my original together have a base of 2A. Now within this picture that I just made, by reflecting that triangle, do you see the big triangle that I made? The two smaller triangles reflected together made a big triangle, and in this corner is 60 degrees, and in this corner is 60 degrees, and along the bottom is 2A, but also along the top, notice how I have a 30 degree and another 30 degree. Together, those make another 60 degrees. Now, what I've created in that big triangle there, or that bigger picture, is a equilateral triangle, equiangular equilateral. So that means that all the sides, in fact, would be 2A here on that big triangle picture. So generalizing back to my blue triangle, which is my 30, 60, 90, that means the hypotenuse of my 30, 60, 90 degree triangle would be, in fact, 2A. Okay, so 2A would be the hypotenuse of that triangle. In fact, it would also go over here as well. So when we see how that relationship works, we can now use the Pythagorean theorem to figure out this altitude here, or this longer leg of the 30, 60, 90 degree triangle. So if I did that, I would say I have A squared plus, let's say I don't know that one, so maybe I'd call that B. I'd say B squared equals 2A quantity squared. So I'd have A squared plus B squared, and then here I'd have 4A squared when I square both parts. Now if I go ahead and subtract the A squared away, it says B squared equals 4A squared minus an A squared would be 3A squared. And now I go ahead and square root to solve for the B. So it says B would equal the square root of 3, and once again, square rooting an A squared gives me an A. So the square root of 3 times A. So what that means is on the longer leg of my 30, 60, 90 degree triangle, I would have the square root of 3 times the A. So this is how the relationship is built and how we understand it. It's by seeing those triangles, seeing how they are parts of other triangles like an equilateral or an isosceles, and then using those relationships help us to find missing sides. So let's go ahead and write this part in your notes. In a 30, 60, 90 degree triangle, you have a 30, a 60, and 90 degree angle, and then our relationships look like this. There are actually two. First of all, the hypotenuse equals 2 times the short leg, and the long leg equals the short leg times the square root of 3. So if you want that visual again on how we derive that, remember that this is the A, this would be the square root of 3 times the A, and then this would be 2 times the A. So the short leg in this case was labeled with an A, and then you can see how the short leg is used to determine the hypotenuse and the long leg. So how do these relationships help us find missing sides? Well, we're going to go through 5 examples now, and you need to copy each one into your notes. They're all a little bit different, okay? So here's the first one. Example 1, this is a 30, 60, 90 degree triangle. So in this 30, 60, 90 degree triangle, we have two variables we need to solve for. Y happens to be on the longer of the two legs, so this is the long leg, and X is on the hypotenuse. So remembering our relationships, let's say we want to solve for X first. X is on the hypotenuse, so I would need a 30, 60 triangle relationship, 30, 60, 90 degree triangle relationship that has the hypotenuse. Well, in a 30, 60, 90 degree triangle, it says the hypotenuse equals 2 times the short leg. Well, in our picture, the hypotenuse happens to be x. 2 times, what's the short leg in our picture? The short leg is 4. So x would equal 2 times 4, which happens to be 8. So I know that the x is 8. Now, if I wanted to solve for y is on the long leg. So I would need that relationship that talks about the long leg. It says the long leg equals the square root of 3 times the short leg. So the short leg times the square root of 3. In our picture, the long leg is labeled with a y. The short leg is labeled with a 4. And then if I just drop down times the square root of 3, it says y would equal 4 square roots of 3. So I can use those relationships to help me find missing sides without having to recreate using Pythagorean theorem. Let's take a look at another example here, example 2. Again, a 30, 60, 90 degree triangle. This time my x is on the short leg. I know it's the short leg because it's across from the 30 degrees, which happens to be the smaller angle. So I have a short leg here that I'm trying to solve for. The only side I'm given is 9, which is the long leg. So I need to use a fact about the long leg, which says the long leg equals the short times the square root of 3. So in our case, the long leg is 9, the short leg is x, and I'm just placing those values inside that formula for the relationship here. So if I needed to solve for the short leg, you'll see that I would need to divide by the square root of 3 to get the x alone. So it would say x equals 9 divided by the square root of 3. But we can't leave a square root or a radical in the denominator. So I would multiply the top and bottom both by the square root of 3. I would get 9 square root of 3 over, remember these two multiply to make the square root of 9, which is just 3. And now if I simplify, 9 divided by 3 here is 3, so I'd leave my answer as 3 square roots of 3. So x is 3 square roots of 3. I'm just going to add that to my picture here. Now once I know the short leg, the other part solving for the hypotenuse now comes. So the hypotenuse equals the short leg times 2, or 2 times the short leg. So in this case, my hypotenuse was y, and if I take 2 times my short leg, which was 3 square roots of 3 now, because we solved for that, my hypotenuse equals, remember you can multiply these two here, giving me 6 square roots of 3. All right, so we've used the 30, 60, 90 degree shortcut. Here's one more, 30, 60, 90. And again, this time I have the hypotenuse, and I'm looking for the short leg and the long leg. So 30, 60, 90 degree triangle, I have the hypotenuse, so I need to start with a fact that involves the hypotenuse. And it says the hypotenuse equals 2 times the short leg. So the hypotenuse in my picture is 6, 2 times the short leg, which is labeled with an x. So again, here I need to solve for x to get x alone, so I'll divide by 2, so x is 3. So I know my short leg is 3. Now, if I know my short leg is 3, the other fact said that the long leg will equal the short leg times the square root of 3. So my long leg is y, my short leg is 3 times the square root of 3. So my long leg is just 3 square roots of 3. So sometimes we have to worry about a radical in the denominator, and sometimes we don't. It depends on what relationship is given and what that relationship is. All right, let's look at a couple 45, 45, 90s here, and then we'll call it good. So in this picture, we have a 45, 45, 90 degree triangle, which means you have two 45 degree angles, and you know a leg here is 10. And now remember, in a 45, 45, 90 degree triangle, it's isosceles. So the fact that this leg is 10 also tells me right off the bat that x will also be 10, because two equal angles means I will have two equal sides, two congruent sides. So Now that I know that, now I can just use the fact that says the hypotenuse will equal the leg times the square root of 2. The hypotenuse is labeled with y, so y will equal the leg times the square root of 2. Now I have already solved for the hypotenuse in that triangle, and I didn't even need to simplify a square root. All right, one more example, example 5. Again, this is a 45, 45, 90-degree triangle. How do I know? Well, the fact that there are two congruent sides that are marked. That means it has to be a 45, 45, 90-degree triangle. So knowing that, and I'm given the hypotenuse here, I can go ahead and set up my relationship. Hypotenuse equals the leg times the square root of 2. Now the hypotenuse is always already labeled with 6 square roots of 2. The leg is either x or y. In this case, it doesn't matter what I put because they're both going to be the same or congruent. So I'm just going to put an x here times the square root of 2. Now, in order to solve for the x, notice he's being multiplied by the square root of 2, so I would divide by the square root of 2 on both sides, leaving my x alone. And over here, notice that the square root of 2 and the square root of 2 will also divide away. So my x is 6. So the x is 6, and that means the y is also 6 because I have an isosceles triangle. Okay, so working with these relationships, knowing these relationships is really critical. So the more we work with them, the more we become familiar with those relationships and know them by heart. So I want to thank you for taking good notes today and getting those examples in and trying to understand that relationship. Okay, thank you. Bye.